Good evening, everyone. This is Abdullah Kareem, the Governor of Saline Water Conversion Corporation, and it's my great honor to be with you this night. In fact, as we are talking about or speaking about the sustainability, we are talking about the future. As we are talking about water, we are talking about life. So we are talking about how we can sustain our life in the future. SWCC is counted as one of the national champion, and it's have a great potential to be a global champion in the water sector. In SWCC, we have a mission that we should serve our nation, our country, with a very reliable and affordable water from the seawater desalination. And it's not limited to that. We are responsible in the past to transmit this water to the country inside our cities and village. While we are talking about future, I'm sure as I'm talking to a scientific, there is so many need to look at the fourth industrial revolution. We are adapting ourselves with the future and not limited ourselves to what's happened in the past. There is big investment in the water sector in Saudi Arabia. We have 32 desalination plants around the kingdom. We have more than 8.4 thousand kilometer pipelines transmit the water from the sea to the cities inside the country. And we have a lot of investment in the human resources. We have a very talented human resources where we are capitalizing on them for any innovation in this sector. There is 6 pillars that we are relying on. The first pillar, for sure, to talk about health and safety and environment. We have to focus on this pillar for the future because we can't afford to find a sustainable resource of water while we are not keeping our environment away from any effect. So within SWCC and within our country, we are caring about the environment, and usually we are trying to bring a new idea to be more friendly with the environment. We are fully comply with the environment regulation, but also there is a potential to be more comply and to be more friendly with the environment. This is what we are trying right now to find a way to commercialize zero liquid discharge, and we are just about to commercialize this. It seems we will not exceed the mid of 2021 without a great news to the world about how to make the zero liquid discharge more affordable and commercialized. More about that, we are caring more about safety, and alhamdulillah, all of our 32 plants and pipeline systems, we record more than 30 million hours without any incident. We are caring about our health and safety that much because we are in the industry where we can't afford to lose our production even a second. The reliability, this is taking us to the second pillar, reliability. For the water resources to be sustainable, we should care about the reliability and how we can rely on any resources. For the seawater industry, we do our best and we capitalize on our engineers to find a way where we have different operation philosophy and different engineering philosophy to keep our plants really reliable and to keep our pipelines really reliable. This is why we invest in the research center, and this is our third pillar. The real sustainability depends on research and innovation. And without research and innovation, you will not create the future. And without engineering development, you will not make this research and innovation alive. So we care about research, innovation, and engineering. And our aim to reduce the cost of cubic meter by reducing the cost of the capital investment, by reducing the cost of operation, by reducing the power consumption. And alhamdulillah, we managed to build our first plant. It was early this year, and it's built by our calibers from the engineering, from the innovation, through the engineering till the installing and the operation. This unit to produce more than 5,000 cubic meter a day, and the power consumption from the intake till we get the water, it's not more than 2.27. It was our dream to reduce the power consumption. Now we realize that there is so many opportunity in the future, and this is a very potential area to invest in, to bring the water with the lowest power consumption. However, we are also focusing on the technology itself and how to reduce the cost of the technology. We have in our research center, as per today, we have so many ideas to bring the efficiency up and to reduce the power consumption. Once we are talking about the current technology, where it's talk about the RO, we have a very potential space to increase the efficiency in the high pressure pump to be more than 89.5, and also the power energy recovery. We are targeting more than 95, 96 for the membrane. We will invest all what we can do from our experience and our engineers' efforts to bring the power consumption on the membrane 20% less than what's in the market today. This is not the end of our story. We will navigate other technology rather than RO. We will keep our eyes open for any opportunity, because if we are focusing on the future, we will manage to find sustainability. The fourth pillar, it's about efficiency of producing water and the quality of water. And this is really good to announce that during COVID-19, we managed to bring our efficiency much up to the standard, because at that time all of our clients, all of our people on their home on the lockdown, and we have to increase our production from the same plants, and we managed to reach more than 99.5 capacity factor and availability, as we are comparing what we produce in 2020 with what we produce in 2019. It's 5% more from the same systems and the plants. So our caliber, they have their philosophy to be adapted within different cases and different emergency cases. So we are relying on our experts and the experience that we gained from 47 years where WCC invest in the water desalination sector. The fifth pillar, for sure, it's economy. And once we are talking about economy, we are talking about private sector, and without the participation, real participation from the private sector, we will not help the economy to be the main driver for this water sustainability. So we try our best to get more private sector from the kingdom or worldwide and participate in the water sector in Saudi Arabia, especially in the water desalination industry and water transmission. This is what we did in the past. By at the end of 2020, we managed to move a good step ahead our schedule by announcing the transmission water transmission company. This mandate was assigned to SWIC, but today we have the willing to split the water production from the water transmission system, just to make our team more focused on their mandate and not to lose any opportunity to reduce the cost or to innovate more technology in the water transmission or water production. The sixth pillar, and this is our main treasury. It's about our human resources. During the 47 years that we work on the water desalination sector, and I believe that SWIC it's one of the main market driver in the past, and it will keep their mission to be a global champion. We did a lot with our human resources. We have very talented people. We think that we have 10,000 employees, and those 10,000 employees, by the technology innovation, they can operate more than what we do right now. And I keep not telling you about the size of our production till the end, because you can imagine that during or in 2016 we were producing 3.5 million cubic meter a day. Today we are producing 5.9 million cubic meter a day, and we have 3 million, a size of 3 million cubic meter a day under construction, where this plant will replace the thermal technology, just to keep our environment very away from any effect. Yes, we are fully comply with the environment regulation, but to have a more clean technology, a more friendly to the environment, it's much better. So we will shift from the thermal to RO, and this 3 million cubic meter that we build right now will replace 1.6 million thermal. It's where it's running right now and operating very efficient. But the only reason to change this technology, not because of the all this technology, but because of the efficiency and environment. So, and also the economic factor, because by changing the technology, we will save much more power or fuel to be used another purpose for our country. It will reach 209,000 equal barrel per day, and we believe that by this innovation, And by this movement, we will reach whatever the global want, because we are looking and focusing and do whatever it's need for the future. And we will keep this momentum. We will keep doing what is necessary for this very sensitive subject. It's alive. Once we are talking about water, we're talking about life. Once we are talking about, again, I'll repeat again, once we're talking about sustainability, we're talking about the future. So our life in the future rely more on the water sustainability. And we are here. We have all the willing to cooperate with home in the world to bring new technology, to bring new efficiency, to bring new idea to make the water much affordable to the world. I'm glad to present this to you, and I'm open for any questions that you might send it to me. Really, I'm proud to be with you. You are the most expert than me in the scientist, and if we rely on the scientists and comparing what they did in the past with what they might did in the future, we will find a very big room for improvement, and it's really rely on you, Sky. So thanks a lot, and thank you for having me here. Thanks for the organizers, and have a good night.
Hello, good morning. I am Jesus Carrera. I am a hydrogeologist that work in the Institute for Environmental Assessment and Water Research, which is part of the National Research Council of Spain. And I am going to talk about recent advances in enhanced managed artificial recharge with the ultimate goal to renaturalize reclaimed water. We all know that we live in a world of water scarcity, that climate change is worsening this, and that especially in Mediterranean areas, the situation is getting much worse. And I claim that managed artificial recharge is the basic tool to increase available water, much more so than direct reuse. Now, what we have worked on in recent years is to improve the behavior, the results of traditional managed aquifer recharge, to basically by adding a reactive layer at the bottom of recharge basins. The reactive layer consists, the recipe is very simple. It only uses natural materials, and it consists of materials to ensure basically two things. One, the retention of suspended matter and dissolved organic compounds. To this end, we add clay, we add iron, we add wood, organic matter. So the wood tends to absorb neutral compounds, the clay tends to absorb organic compounds, and the iron-3 will tend to absorb anionic compounds. And also, the organic layer adds dissolved organic carbon, which favors that we reach a broad range of redox states. And this is important because different contaminants degrade under different redox states. Another thing is that we let plants grow, and we let plants grow both as a long-term source of organic carbon, but also to prevent clogging. Plants, the roots of plants keep opening paths for the water to flow. And they are also beautiful. So from a social acceptance point of view, plants also help. Anyway, this is what I'm going to talk about. We have built a pilot site to test this concept, and I'm going to share with you the results we have obtained in terms of contaminant removal, pathogen removal, clogging, and the implications that this has on our future challenges. So basically, the idea is that, yes, long residence times, we have known for a long time that a broad range of redox stages favors the removal of all kinds of contaminants. I am putting this figure, which I have modified from Christensen in 2000, 20 years ago, showing that water coming from a landfill loaded with all kinds of contaminants, organic contaminants, 300 meters downstream, contains virtually no contaminants. All recalcitrant species are gone, because the microbial communities developing in these different redox states, well, each of them favors the elimination of different compounds. So it is known that water quality improves during soil aquifer treatment, but our goal is to go beyond that. And so we add this reactive layer, and we tested it at the wastewater treatment plant in northern Spain. You can see here this is where we are. Barcelona is further down, some 100 kilometers to the southwest. And basically what we did is to build 6 canals, which I am showing here, which represent the aquifers, and 6 pilot recharge basins. So these recharge basins, about 3 square meters, and then 6 canals downstream of these recharge basins, 15 meters long, to emulate the aquifer. And basically what we do, this is a photo of the system, the 6 tanks, T1 to T6. And what we have is several these lines, A, B, C, display the points where we sample to compare how the quality of the recharge water evolves along the aquifer. And in these 6 tanks, we have slight variations in the recipe. In the first tank, we have no plants. In the second tank, we just have sand, no layer. And basically what I'm going to do is to compare the performance of T3 to T6, actually only one of them, with a reference without layer. So basically what I am going to show you are the results of the inflowing water, the water that we enter here, which is the outflow from a wastewater treatment plant, from the secondary treatment. So we recharge that. We sample just beneath the reactive layer, and then we are going to sample the effluent. We have more data, but I am going to show you only this. Well, first, of course, when you put water in a sunny environment, plants grow, so the system is beautiful. Lots of plants everywhere. In fact, we have to fight to keep this first tank without plants. Second thing is that the system is working in the sense that we do have a sequence of redox states, and this we can see because you see oxygen drops in the reactive layer, later builds up by the dissolution along the aquifer. Iron increases, which shows that, you know, iron 3, ferric iron is non-soluble. So the fact that we have iron means that we have had iron reduction. So especially during the reactive layer, dissolved organic carbon increases because the reactive layer adds organic carbon, but then drops later because basically the organic carbon is consumed during degradation. And same thing with manganese. Manganese builds up, which means that we are reaching manganese reducing conditions. Like for iron, manganese is only soluble when reduced. So yes, we are managing to get a range of redox states, which is what we wanted. And we can see that here I'm showing the degradation rates, and basically the degradation rate in the layer is this brown thing. Below the layer is this light brown, and you can see that the degradation rate for different compounds, carbamazepine, hembrofisol, these are pharmaceuticals, is 1 or 2 orders of magnitude in general, 1 or 2 orders of magnitude larger than the largest degradation rates observed in the literature for artificial recharge projects. So basically, the point is that yes, the reactive layer is helping, is accelerating dramatically the degradation rate. It is also improving the retardation, which is not surprised because basically we added the organic matter and the clay, etc., to increase the retention time by increasing absorption. So sure enough, retardation should be increased. And again, we increase it by a factor of 10 or 100. And therefore, it should not come as a surprise that we are improving the removal of emerging contaminants. And here, what I am showing here is the removal efficiency in gray for the reference layer. This is without a reactive layer, and in green and brown for 2 different reactive layers. Of course, the reference layer, water quality improves significantly during conventional managed artificial recharge, and you can see that for different compounds. So these are ultraviolet filters, pharmaceuticals. This is the total. We were analyzing some 50 emerging contaminants. So yeah, the traditional system removes some 60%. They improved. Well, this was at the beginning of operation. Later on, it's variable. It decreased for ultraviolet filters. For some others, improved. But in general, the presence of the reactive layer improves things with respect to the conventional, to the traditional managed artificial recharge. Therefore, adding this reactive layer helps. Pathogens are also significantly reduced. Again, I am showing here now this graph is different. So these 3 columns represent the inflow and 2 different tanks. And 2 different sampling points. The leftmost is for the reference without barrier, and the other two are with 2 different compositions. In the middle one is by adding compost as a source of organic carbon, and the last one, the one to the right, is for wood chips. And you can see that all of them reduce pathogens significantly. In this case, the reactive layer does not perform better than the traditional managed aquifer recharge. Both traditional without reactive layer and with reactive layer reduce dramatically the pathogen indicators. In the case of coliforms, by some 3 to 4 orders of magnitude. In the case of Escherichia coli, is about 5 orders of magnitude. You can see that a portion is reduced during between the first is input, second is downstream of the reactive layer. So the reactive layer does improve, but most of the retention occurs in the aquifer underneath. So this is the traditional filtration mechanism that all hydrogeologists know about. So pathogens are significantly reduced. The plants also help. Remember that we wanted to keep plants as a source of organic carbon, but also as to ensure that the system doesn't clog. And indeed, it doesn't clog. You can see here, this is a perspective after some 3 months of continuous recharge. So during 3 months of continuous recharge, the systems did not clog. They did not clog. The only ones that clogged a little bit are the tank one, which had no plants. This is a photo in the winter of 2018 and the spring of 2018. This photo is of August 2018. So the one without plants clogged is this one. The one without layer also clogged, but the remaining did not clog after 3 months. So from a practical point of view, keeping the plants, which is very easy, you have to do nothing. Plants grow naturally. We have tried with letting plants grow naturally. In fact, it was very difficult to keep plants out from this tank one because we had to remove them because they tended to grow naturally. Anyway, the plants help in preventing clogging. And we think that we can improve further. I mean, we are reducing pathogens, we are reducing emerging contaminants, we are also reducing antibiotic resistant genes, which I have not shown, but I think we can do better. So what we are going to do, since our barrier, I showed you that we are managing to get reducing conditions and we have a high iron concentration, our goal is to basically introduce aerobic conditions downstream here in point 2 by pumping the water, doing some air stripping and re-injecting it. Basically, the goal is that in this process, we should precipitate iron, which should favor reduce basically the retention of pathogens and the removal of contaminants. So this is something we are going to test. We have not tested yet. We also want to increase the unsaturated zone. A problem we have with this pilot system I showed you here is that the unsaturated zone is very, very small. We have no room. And we know that pathogens will be retained in the unsaturated zone. So our goal is increase the unsaturated zone, precipitate of iron to favor retention process, and also to try different types of organic substrate at different types of sorting surfaces. And we are going to try the charcoal and perhaps also some metal additions to improve further. So in summary, well, managed aquifer recharge has always helped in addressing water scarcity, and basically water which would not be of good quality and that had to be disposed of into a river can be reintroduced in the water cycle and therefore can be considered an extra resource. Actually, another issue I haven't entered, but which is also relevant, is that by reintroducing this water in the aquifer instead of disposing of it in the river, basically you help the river to become connected with its alluvial aquifer and therefore to work as a river. So by doing this, not only you improve the water quality of the recharged water, but you also help in the river, in recovering the river, so that the river starts providing environmental services. So all these were advantages of the traditional managed aquifer recharge, but what we say, and what I have tried to show you, is that it can be improved by adding this reactive layer. Very simple, just sand, wood or compost, a little bit of clay, a little bit of iron, and that this reactive layer helps in reducing dramatically organic pollutants, pathogens, and antibiotic-resistant genes. We are also testing, sorry for the typo, we are also testing for microplastics. We don't have results yet, but I am convinced that we will reduce dramatically microplastics, and that there is plenty of room for further improvement by changing the composition of the layer, by increasing the unsaturated zone, by doing aerobic conditions downstream. So I am convinced that with what we have done and with these further improvements, eventually recharged water will be undistinguishable from native natural water, and therefore it can be considered renaturalized water. So reclaimed water, after going through all this process, we hope it can be considered natural water. And that's all I wanted to talk to you. Thank you very much.
I'm going to be talking about the importance of heterogeneity. I am the proud awardee of the 9th ICWRAE prize in groundwater, and I have been working on groundwater for the last 35 years. And one of my main interests is in how to characterize heterogeneity of the underground. I will be talking about heterogeneity, and even though we all understand that in the subsurface the materials vary in space in a more or less heterogeneous way, we may not have an exact idea of what we mean by that. I mean, which type of heterogeneity are we talking about? It is, in general, not possible to see what's in the aquifer. I mean, what is underground. I mean, we can drill wells and see a little bit what's beneath the surface, but in general, we don't see what an aquifer may look like, except for some cases, like when we have access to an open pit mine. In this case, this is the Hunter Valley Coal open pit mine. It's a picture taken there. For reference, there is a crane here that may be 10 meters high. You can also see the trees on the ground. So this section could be maybe, I don't know, 100 meters thickness. And here we can see actually what the underground looks like, what is beneath the surface. And we can see that there are many materials that you can differentiate by the colors in the picture, and you can see that there is some layering. I mean, this is a sedimentary basin, so there is variability in the vertical direction, but there is also variability in the horizontal direction. So there is this heterogeneity, these changes that exist underground. But as I said, in general, we don't have access to this information. We don't have an access to this picture of our aquifer. The most we may have is a couple of wells. Okay, the most we may have is just information about the distribution of the different materials at a couple of locations, a few wells in the aquifer, and we are going to be seeing only what you see in these small slits. And from that, we should be able to reconstruct the heterogeneity that is beneath the surface. Because if we don't account for this heterogeneity properly, as I will show you next, we can make, it is very possible that we will make predictions that are not accurate, that are not good. I mean, we're going to make an analysis of how the aquifer may behave, that it will be wrong. Sometimes, besides this couple of wells, we may have some seismic information, some geophysical information, like a seismic survey. And in this case, I'm showing you what could be, say, the result of this seismic survey. And what you see here is a normalized impedance. And you can relate this impedance with some of the parameters that will describe the aquifer. In general, it's more related to the porosity or to the water content. That's what you can relate this information to. So we have very limited direct information, a direct vision of what's underneath through the wells, and some approximate information of what may look like the heterogeneity through some secondary geophysical information when we have access to it. But again, at the end, what I want to do is to model this heterogeneity from that limited information. Because, as I say, if we don't model this information, we don't model this heterogeneity, we may end up with poor predictions of our models. And I'm going to show you a few examples, yes, to show you the impact of accounting for the heterogeneity in the modeling of the aquifer. The first example is just imagine we have a release of some contaminant, some solute in the aquifer. Water is flowing from left to right, and we have 4 different aquifers with four different representations of heterogeneity. On the top we have, say, the easy model, the one which is homogeneous, the one which is still being applied very much today, and then we have three more aquifers with increased amount of heterogeneity, which is measured by the variance of the log conductivity. So let's see how this solute behaves when we dump it in the aquifer, depending on the heterogeneity of the aquifer. You can see that in the homogeneous one, basically the dump moves like a blob, I mean like a compact mass of contamination, whereas as soon as we have heterogeneity, this plume will change in shapes. I mean, it will elongate depending on where is located the areas of highest conductivity, and some of the mass will be retarded because it will be trapped in the areas of low conductivity. So you can imagine that, I mean, if the reality is like any of the heterogeneous aquifers that you see here, the predictions that you are going to be making when you use a homogeneous aquifer are going to be very, very far-fetched from reality. And some may say, well, but I mean, generally in groundwater transport, flow and transport, I mean, there is also dispersion induced by the variability of the velocity of the water underneath, and here you haven't accounted for that. Okay, let's see in another example. I mean, what happens if we put this dispersion, this macro dispersion as its model, and in the left it will be just a simulation of the movement of the solute in the aquifer, and in the right will be an equivalent homogeneous aquifer with some macro dispersion to try to mimic this variability, this elongation of the plume that we observed in the previous picture. And this is what will happen. I mean, yes, the macro dispersion model elongates the plume in the homogeneous case, but still, I mean, the image, the understanding, the representation of how the solute behaves in a homogeneous aquifer, even including this macro dispersion, is very far from the actual movement of the plume in the heterogeneous aquifers. And we can see that, I mean, the more heterogeneous the aquifer is, the more dispersion, I mean, the more variability, the more dispersion, both lateral and longitudinal, there is on the final plume, and the plume just breaks apart into smaller subplumes that will never be captured if we do a modeling of a homogeneous aquifer. One final example, imagine that there is an area that has been polluted. In this case, it's a fictitious square area that has been polluted. On the left, we have a heterogeneous aquifer. On the right, we have a homogeneous aquifer. If we try to clean it, and we just use a pump and treat approach in which we will be pumping out the water that has been contaminated in the aquifer, this is what will happen when we start pumping. We see that in the homogeneous aquifer, everything basically moves very smoothly towards the pumping well, which is at the center, whereas in the heterogeneous aquifer, because of this heterogeneity, which implies areas of low velocities and areas of high velocities of water, well, everything is much more intricate, is much more complicated. Water doesn't flow so easily towards the aquifer, and therefore the solute is not extracted, is not taken out so easily. In the homogeneous case, apparently, I mean, you will be able to clean up the aquifer in a relatively short time without any problem. And this result is the reason why many pump and treat approaches fail, because they did the modeling, they did the analysis of how the pump and treat will work using homogeneous aquifers, when the reality is quite different. Inverse modeling is a way to try to try to track back, which is the heterogeneity of our aquifers. And this is what we have been working for the last, I don't know, 20 or 30 years in our group, and this is also the reason why I got the award this year. By inverse modeling, basically what we are going to be doing, what we try to do, is to gather information from the state of the system. And in an aquifer, we are talking about hydraulic heads and or concentrations of the solutes. And with that information, which generally is easier to obtain that measuring hydraulic conductivities, then we will try to infer the spatial distribution of our parameter. I'm going to demonstrate you this inverse modeling in a forensic hydrogeology case, which is the identification of a contaminant source. So we are going to be trying to get both the characterization of the structure of the aquifer, of the heterogeneity of the aquifer, and also identify where a contaminant was placed in the aquifer and when that happened. So the data we will be using to perform this exercise will be concentration breakthrough curves at some sampling locations. In an aquifer that I'll show you next, we'll put some observation locations. We will see how the solute gets through those locations, and with only that information, so several breakthrough curves at different locations in the aquifer, we are going to be able to retrieve back the heterogeneity of the aquifer and also the location, the strength and the duration of a point contamination, a point continuous contamination. We did this with a laboratory experiment, and we basically in the lab we built a synthetic aquifer. You can see here how they were putting together two different types of materials. In this case, they were glass beads of different diameters, and at the end they built this heterogeneous sandbox with, you can see there, two types of materials. The darker one is the most conductive, and the lighter one is the less conductive. They are the smallest sphere beads. A close-up of that sandbox, you can see it here. And the heterogeneity in this case, I mean, is not what we saw in the open pit mine, but it's clear that there is heterogeneity. In the dark spot that you see there is where we will be injecting the solute, and this solute is clearly that is going to be displaced initially through the high conductivity area, which is this darker area, and then it will have to move. I mean, the water flows from left to right. From right to left. And then it will look its way to the exit point, which is on the right side of this sandbox. A schematic view of the sandbox. We have basically a constant stream, constant hydraulic head on the right border of the sandbox, and another constant hydraulic head on the left border of the sandbox. So the water goes from right to left. The values are, well, I didn't put there, this HU and HD, and the size of the sidebox, as you see there, is about 95 centimeters in width and 70 centimeters on height. At the location of the red triangle, we will place the injection, and then we will observe the breakthrough curves at the dots, at the black dots that you see on the figure. And from that information, from the breakthrough curves at those observation points, we will be able to retrieve both the architecture of the sandbox and also the location where the release happened, the time when it started, when it ended, and the strength of the injection. We use fluorescein, and on the other side of the sandbox there is a dark room with a camera, so that when we inject this fluorescein and we excite it with this blue light neon, then what happens is the fluorescein gets just fluorescent, and the amount of or the color that you get back will depend on the concentration of the fluorescein. This is an example. This is one of the pictures that will be taken from this dark box with the injection point, as I mentioned, and you see this yellowish greenish fluorescein being captured by the picture. Again, the intensity of the color is calibrated, and we can retrieve from this picture, on the basis of the intensity of the color, the concentration of the fluorescein at any location. And as I said, we are trying to mimic a case in which we have these 25 observation points, and we are looking at the breakthrough curves at those 25 observation locations. The experiment that we carried was the injection of this fluorescein at 20 milligrams per liter during 1200 seconds. We took those 25 black dots observations every 30 seconds until 3000 seconds. And there were 25 observation points, and the inversion approach, the inversion modeling that we used was this ensemble Kamal filter. And I show you how, the results that the ensemble Kamal filter produces. The ensemble Kamal filter is an assimilation filter, it's an assimilation approach. So what happens is that we take every 30 seconds one snapshot, values at the 25 locations of the concentration, and with those values we will try to estimate the parameters of the model, basically the heterogeneity of the conductivity and the source characteristics. The ensemble Kamal filter is like you are running in parallel. You have a model, a numerical, conceptual model that you have built, and then you have your observations. So in every 30 seconds you stop, you take observations, you compare the observations with the predictions of the model, and then you correct your model depending on how well you are making the predictions. Okay. So these are the results that you get. The final estimation of the conductivity that we obtain, which is made in a very fine grid. As you can see there, we're making estimates of the conductivity in a very fine discretization of the sandbox. Well, basically, it's capturing this structure of the high values and of the low values of conductivity. It's clear that we are not getting back exactly this binary heterogeneity that is actually in the sandbox, but it's clear that we are capturing the heterogeneity. And we are also able, for instance, to identify the coordinates of the release. As I mentioned, what you have here is the estimate of the X and Z coordinates of the release as a function of time. And because of the way the ensemble Kamal filter works, what you have is actually as a band of estimates, is a range of estimates that is given by these box plots, with the red line being the mean value, the best estimate of the location. And we can see that both for the X and the Z value, we are getting almost exactly back the position where the injection happened. The same we did it for the initial time, the final time, the release amount, and obtaining good values after some time steps, after some of this updating of the model every 30 seconds. With the parameters that we obtain, with the location that we obtain, we identify, and with this structure of the conductivities that we identify, then we try to make a prediction of how the plume will behave. And the truth is that the results are very satisfying. This is the true plume, as observed in the pictures that we took in the dark room. And this is the estimated plume obtained with the model built using the estimation given by this inversion method, this ensemble Kamal filter. Let me show you again. This is the true plume, and this is the estimated plume at different times, at 10, 40, 60, and 90 seconds since the beginning of the injection. So I will conclude that heterogeneity, as I have shown you, plays a crucial role in the fate and transport of solids in groundwater. It has to be properly accounted for if we want to make predictions that make sense. Improper modeling will result in an improper remediation strategy. And the tools that we have right now that will allow us to capture this heterogeneity, some of these tools are these inverse models that will allow us to improve the characterization of the subsurface, making use of easy to gather information, such as could be piezometric heads or concentration at observation locations. That's all. Thank you very much.
So I am Professor Abdelkader Al-Arabi, a previous winner of the prize in the groundwater section in 2006. So I would like to thank the organizer for this opportunity to gather all the previous winner to present their research work in this special conference. So my contribution today is to give some new insight to the development of research on the vulnerability of the coastal aquifers. So my presentation is on quantitative evaluation of the vulnerability to seawater intrusion in coastal aquifers using a new normalized groundwater age-based index. And we will give also the implication of this method for management and risk assessment. So what are the strong points of this method? So this method is based on coastal aquifer modeling for quantitative mapping of seawater intrusion vulnerability. So it uses also steady state concentration and mean age of salt water as a weighting term. The concept of the zero vulnerability line or surface is introduced for the management of water resources in coastal aquifers. And also we will give the advantages of this approach, which will be highlighted using the Henry problem and an aquifer from the Mediterranean Lebanon. And also we will conclude with the implication of the method for coastal aquifer management and risk assessment. So as well as you know, there are the vulnerability assessment was introduced a long time ago by Marga in 1960-68, and it was developed by several authors later on. And the vulnerability can be intrinsic or can be also specific. And behind this, there are several methods that have been developed, which are analytics, and some are also indexing like drastic, broad, syntax, epic, COP, etc. And we can also use the numerical model for the assessment of the vulnerability. For seawater intrusion into coastal aquifer, and specifically, there are some methods which can be analytics, like, for instance, the work of Werner in 2020 or 2014. And also there are some indexing methods like GALDIT, which is too much used with several variations. And also we can use some complexity models, but until now, there is no physical methods before this work. That's why we are introducing this work in order to quantify the assessment of the vulnerability. So since GALDIT is too much used, when dealing with seawater intrusion, we will try just to give an idea and remind the index that are used. That means the 6 parameters, such as the groundwater occurrence aquifer type, the aquifer hydraulic conductivity, the groundwater level with respect to seawater level, and the distance from the coast, the impact of seawater intrusion status, and the 6th parameter is the thickness of the aquifer. So at the end, we have to calculate the GALDIT index, and we have to map it through, for instance, through the GIS, and we will classify it in high vulnerability when it is more than 7.5, and it is moderate when it is between 5 and 7.5, and we have low vulnerability when it is less than 5. So we applied this GALDIT method, which is very qualitative. Here we can see, here in Morocco, you can see already the 6 parameters maps that we used for this GALDIT, but the result is here. As you can see, we have here the GALDIT specific vulnerability map of this coastal aquifer, and we can see that the result revealed that the fringe area of this aquifer, which are the most affected with seawater intrusion and with a high risk in the northwest part of the study, which is a subject of oil field pumping groundwater for drinking supply. So we compared this Galdit method result to the numerical model that we used, and we can see that there are some similarity between the result, but the numerical model gives more details on the distribution of the concentration in the area, and we have the area which is intruded by seawater intrusion, while for the Galdit method we can see only some only moderate or low or high vulnerability without, for instance, more insight or more details on the seawater intrusion and the extent of seawater intrusion. So the Galdit method was also used in several areas in the world, like for instance in Finland, where we use this Galdit method in order to combine it to climate change. So the vulnerability of coastal aquifer, you see it is defined through the process of seawater intrusion. So for this process, we can define the density stratification within the depth, and we can also define the dispersion zone and the submarine discharge zone near the sea. And we can see that that salt water can circulate in this zone, coming from the seawater and entering to the zone of the dispersion and coming back to the sea. When we manage the groundwater in coastal aquifer through, for instance, a pumping well, we can have what we call the condo of depletion, because we have the groundwater level depletion, and we can have the upcoming from the bottom. We can have some buckling, which is very risky for seawater intrusion. Why we have to assess vulnerabilities to water intrusion? Because we need prevention tools against seawater intrusion for the management of coastal aquifer. And also we need to prioritize short-term remedial actions. So as Galdit methods and other techniques have some limitation, we need to really to present this limitation. For instance, there is no consensus for the selection of the correlation variables. And it is also impossible to quantify the water balance, including the submarine discharge into the sea. And also we make a lot of errors which are induced by data interpolation. And the mostly, which is the vulnerability maps that are primarily 2D and not representative of the salinity and also the density, the stratification process. And the most important also limitation is the assumptions behind Galdit, which are not universal example of heterogeneous aquifer and karst aquifers. That's why we need for a new method based on physical approaches and efficient numerical models, simple or simplest. So the new method that we are going to introduce to you is it uses stationary model for flow and mass transport with variable density. The distribution of salinity in steady state cannot be used directly for the vulnerability assessment. The age of the salt water is used as a weighting factor for the salinity field. And we construct a standardized vulnerability index, which is calculated at cell of the numerical model. And from this, we will deduce and also introduce what we call the zero vulnerability level or the zero vulnerability area. And we will also test that the correspondence of this vulnerability level zone is not confused with the 50% isochlor. And finally, the method is independent of the spatial discretization, finite element, finite difference, or finite mood, and may be substituted on modeling tool available in the community. So the new method is based on the two equations: the mass conservation of the fluid, the mass conservation of the salinity, and the generalized Darcy law, and also the density concentration relationship, since we are dealing with seawater intrusion. And on the other hand, we have also to calculate the average age of groundwater following this equation and using also this boundary condition. And we combine all these equations with the average age of groundwater. We can introduce this normalized vulnerability index, which is equal to 1 minus the age divided by the maximum age and multiplied by the normalized concentration. This is the index that we are using for this vulnerability method. And this method was verified and illustrated through different examples. So we use this academic problem of Henry 1964, which is proposed initially to verify numerical models. So for here, we resume to illustrate the normalized vulnerability index and the zero vulnerability concepts. And we will see also how does this zero vulnerability line compare to 50% isochlor. So this in the first cases of the Henry problem, we can see already the result here. So on the left, we can see the distribution of the concentration, and we see also the vulnerability zero line, as we can see here, which follow exactly the 25% isochlor. While on the left, we can see already the distribution of the vulnerability index, and we see all this zone. The zone which is vulnerable to seawater intrusion is this, which is given by this distribution of the vulnerability index. And if we apply the GALDIT, it predicts the same vulnerability distribution according Z. This is another problem. So the second case is the same problem of Henry, but with the pumping well, which is located here, and with this flow rate. So we can see already that we have some advance of the vulnerability index area due to the pumping well. And look here that the zero vulnerability line is located between 25% and 50%. It moves a little bit. So the third case is the same Henry problem for homogeneous case, but we increase the flow rate a little bit, and we see already that the vulnerability, as you can see from the left, that the vulnerability area moves a little bit, and the zero vulnerability line, really, it is located very close to 75%. So for the third cases for the energy problem, so we use a little bit we varies the hydraulic conductivity and through exponential decrease, and you can see following this formula, and you see already here the distribution of the concentration and the zero vulnerability line, which is around 25%. While on the right, we can see the vulnerability index, which is, we can see it is as completely different from the example that we given before. So in the same time, we decrease in this time the hydraulic conductivity exponentially. So it's grow within the depth, and we see already here the distribution of the vulnerability index, and the zero vulnerability, which is completely different, is not within 25%, nor with 50%. So it means, and this is a reference of the vulnerability. We can take it as a reference, which is very, very good example. So let us, for instance, apply GALDIT. It will predict the same vulnerability distribution in both cases. For instance, the cases that we have seen before, it will give the same. So which is not the case. Look, for instance, the results here are completely different than result in the second cases. So at the end, we have applied the method to a field application in Lebanon. So this area, it is used really, we have increase of water demand of drinking water, especially for immigration there from Syria, and also the water is used also for agriculture. So we examine here several short-term management schemes by comparing vulnerability maps, and also we demonstrate this using the cross-section here, A primes, and we will see the result in the next slides. So we'll see here the cross-sections, and we have the pumping wells here. So the cross-section, we have 6 distinct hydrological units, and we have also all the input, such as, for instance, the recharge, and we have the recharge, lateral recharge. We have the pumping well with the discharge of 579 liters per hour, and the second pumping well is 600 liters per hour, and the filters are located for the pumping well number 1 at 45 meters, and the second at 30 meters deep. The wells are located also 1,500 meters from the coast, and the second is at 3,000 meters from the coast. So the result is given here. So we will see that the pumping well number 1 is already located in the vulnerability index area, and we can see it here because the zero the zero vulnerability line is located here, as you can see. And we can say already that the vulnerability to seawater intrusion increased within the depth. And the vulnerability gradient increased when approaching the coast. And the zero vulnerability delineates a risk zone of approximately 2,740. And the pumping well number 2, which is a little bit beyond the vulnerability index zone. So we try to see how we can solve the problem and make this zero vulnerability zone a little bit less with less area. So there are several solutions. For instance, we can move the wells in X, Y, and Z. We can also decrease the density of the wells, and we can reduce the pumping rates. We combine all these three actions with a pumping well, which is located between pumping well number 1 and pumping well number 2, and we reduce a little bit the total of the flow rate by 20%. So the results is here. So the zero vulnerability delineates a risk of zone approximately only 750 meter, and we have 1/3 of the aquifer space will no longer be under the threat of saline intrusion, as you can see here. So through this example, we have this demonstration of the usefulness of the concepts introduced for the operation and management of the coastal aquifers. So as the implication of the method for the management of coastal resources, we can say that the zero vulnerability line concept is a new communication tool on seawater intrusion and the impacts of the global changes. And also we can have rapid assessment of the risk associated with the planning of management schemes. We can also prioritize the wells according to the risk of salinization. We can also facilitate the construction of DSS in our operational setting. And also we can have a parametric or conceptual uncertainty, which can lead to stochastic description of the zero vulnerability line. So we can also accelerate the simulation optimization approach by using, for instance, by use as a twin models of the couplet transient model. So we can also use as objective function is to move, for instance, the zero vulnerability line back towards the coast, as we have seen in the example of Lebanon. And also it plays a role in the optimization of the monitoring system and the frequency of the measurements. So we can say at the end that the method does not require continuous measurement of the concentration. So as a conclusion of this research, we can say that the new approach is reconciling vulnerability mapping in coastal aquifers with advanced practices for modeling variable density process. Also, the normalized vulnerability index is obtained from the salinity distribution and the mean age of salt water in a stationary regime. So it is also in homogeneous aquifer or with heterogeneous stratification, the vulnerability increase with the depth. And this behavior cannot be reproduced by the previous techniques, such as, for instance, the Galdic methods or other techniques. So the zero vulnerability line delimits the risk area. This new concept has important implication for optimal water resource management and risk assessment in the coast. So the zero vulnerability line is not to be confused with 50% isochlor, as we have seen through different examples, which is not a robust metric to assess the risk of marine intrusion. And finally, we can say that the theoretical and practical example provided demonstrate the relevance of this approach to classify, compare, and validate the different coastal water resources management scenarios. So at the end, I would like to give special thanks to the contributor of this research, as you can see their photo here, which are from Belgium and from Lebanon, and also from Morocco. So thank you for your attention.
My name is Wolfgang Kinzelbach, and I would like to share with you some ideas and results from a Sino-Swiss groundwater project. I'm here talking for a whole team of people, and my talk has 4 parts. First, I want to introduce the situation of overexploitation of aquifers worldwide, and in the North China Plain in particular. After that, I define what I mean by sustainable groundwater use, Then I turn to a management system for one particular county in the North China Plain. And finally, I come to some results and conclusions. NASA and the German Geo-Research Center in Potsdam have been measuring the gravity field of the Earth since 2002 with a pair of satellites. They found that the mass distribution over the globe is changing in time, both seasonally and over longer times. These local mass changes are caused by the redistribution of water. The changes are expressed in centimeter of equivalent water loss or gain, and the map shows in red tones the regions where water mass decreased, and in blue regions where water mass increased between 2004 and 2020. Melting glaciers show as decrease, like here in the Arctic and Antarctic regions. But depletion of aquifers also shows as red, like here in California or in the High Plains Aquifer in United States Midwest. Then, of course, in Saudi Arabia. In Pakistan and India, it's a combination of glacier melt and groundwater overpumping. But here, in the case which you are interested in this lecture, the North China Plain, the mass decrease is clearly due to overpumping of the aquifer system. On the whole, the world pumps about 1,000 cubic kilometers per year of groundwater, and about 1/4 is not sustainable. Now here's the North China Plain defined by the boundaries like Taihang Mountains in the west, the Yanshan Mountains in the north, the Bohai Sea in the east, and the Yellow River in the south. It is an area of about 140,000 square kilometers with more than 6 million groundwater wells. You can find yourself the mass loss in this region with NASA's data analysis tool. If you put a rectangle over the North China Plain, you find a decrease of the gravity signal equivalent to 2.4 centimeters of water column per year between 2004 and 2020, which translates into a mass loss of 4 cubic kilometers of water per year. Now, on the ground, you see the decrease of storage in the observation wells all over the plain. Here is a typical one, which has been declining by 80 centimeters per year since 1980. If we use a specific yield of 3%, we can nicely superimpose the gravity curve and the Pearson method data. The distribution of overpumping in the plain is quite heterogeneous. The aquifer system is usually divided into a shallow phreatic aquifer here on the left and the deep confined aquifer on the right. While the main pumping occurs in the shallow aquifer with the cones of depression in the Piedmont area, the drawdowns of groundwater are more serious in the deep aquifer. Due to its smaller storage coefficient, a smaller amount of pumping produces a much larger drawdown. Of all abstractions, about 63% are by agricultural irrigation and 37% for households by household and industry. Now, what is the reason for overpumping? The North China Plain is China's breadbasket. It produces 21% of the national wheat output and 13% of China's maize crop in a double cropping system of winter wheat and summer maize. This intensification started in the 1980s when China's population increased fast and more people had to be fed. One has to know that rainfall in the North China Plain is concentrated in summer, the monsoon season, and is usually sufficient for the summer grain crop, which in a normal year needs at most one irrigation. But the winter wheat growth season is just a part of the year here with very little precipitation. So it has to be irrigated fully. While natural rain supplies about 500 millimeters per year, the combined need of wheat and maize is 800 millimeters. So 300 millimeters of irrigation are needed on average. In the dry season of the year, streams have little to no water, so the irrigation basically relies on groundwater resources. The question is, can one go on like that? There are three ways in which groundwater pumping can come to a stop. First, there is the physical limit when the aquifer is pumped dry. The second limit is the economic limit, which means water levels are so deep that the cost of pumping water becomes excessive for irrigation. And the third is the quality limit. Usually, water is the more mineralized, the deeper we go. Once the mineralization increases to a degree which makes the water unusable, we also have to stop pumping. But long before we reach any of the three limits, there is a number of undesirable consequences of overpumping. Let's start from a high groundwater level, which gradually declines. The first phenomenon encountered is the decrease of stream flow. When the groundwater level falls below the stream bed, the stream does not receive groundwater anymore, and in the dry season, it falls completely dry. In the North China Plain today, groundwater tables are usually already deeper than the riverbeds. Wetlands suffer from falling groundwater levels. Hebei province lost 90% of its wetlands in the last 70 years. A falling groundwater table leads to die-off of phreatophytic vegetation. That is vegetation which relies on the groundwater table for its water supply. A famous example in China are the desert poplars of Xinjiang province, which experience severe degradation due to declining groundwater levels. The next thing which happens is soil subsidence. It's up to 2.5 meters in a wide area in Hebei province. Crevices and holes in the ground develop due to the settling, and 50 such features are longer than 1 kilometer. Close to the coast, a cone of depression will attract seawater and you get saltwater encroachment. Finally, the depletion of storage makes the system more sensitive to climate change. As large storage is an insurance. Even for multi-year droughts, with storage depletion, this insurance is lost. Having seen all the consequences, what is the correct way of using groundwater? There are internationally recognized best practices. I summarize them in 4 items. Pumping should stay smaller than recharge to prevent systematic decline of groundwater levels. Groundwater should be used conjunctively with surface water. It should serve as a buffer which stabilizes water availability also in drought times. The groundwater table should stay between 2 red lines, which I'm going to describe in more detail in the next slide. And finally, we can increase recharge by managed aquifer recharge. Whenever we have excess surface water, we can infiltrate it into the groundwater for later use. Unfortunately, pumping water is much easier than putting it back into the underground. Now, the red lines concept. It prescribes an upper limit and a lower limit for groundwater levels. Groundwater levels should move in between the 2 red lines. So management tries to keep them there. The upper limit is important in agricultural areas. When groundwater gets too close to the surface, it causes waterlogging and phreatic evaporation, which in turn leads to soil salinization. In the North China Plain, a depth of about 5 meters is advisable to prevent phreatic evaporation. The lower level also depends on the specific needs of a region. If phreatophytes have to be protected, it should respect their maximum root depth. If stream flow has to be protected, it should not fall below the stream bed. In an agricultural setting as the North China Plain, other criteria are important. A declining groundwater level leads to loss of well yield. That implies that the time needed for irrigation becomes longer and longer, and possibly it's not sufficient to satisfy all the plants' need in time. Also, to combat droughts, you want to leave a certain storage reserve. In the county we are going to look at, 30 meters below ground would be a reasonable lower limit. Now, returning from overpumping to sustainable use in the North China Plain means that on average, less water can be pumped. So the bad news is that all other things being equal, agricultural irrigation and therefore crop production has to decrease. The good news is that due to the buffering effect, production is rather uniform over the years, even in drought years. Note that it may be possible to correct fluxes and reach an equilibrium of fluxes in a relatively short time of a few years or a decade, but that just guarantees that things do not get worse. If we want to raise groundwater levels, it takes much longer time to undo the result of the last 50 years. Now, the global analysis of the whole of the North China Plain is too crude for planning local countermeasures. For that reason, we now analyze a single county, Guangdao County. It's located in the south of the North China Plain with an area of 456 square kilometers, an irrigated area of 300 square kilometers, and a population of 365,000 people. To get into equilibrium, groundwater abstraction in the county has to be reduced by 20 to 25%. There are 3 measures available. Number 1, water saving and irrigation, and a radical version of this would be the return to rain-fed agriculture, fallowing of the winter crop, and increased import of surface water from the south. Let's look at the aquifer system. The shallow aquifer is about 90 meters thick, then an aquitard of about 100 meter thickness separates it from the deep aquifer, which is about 200 meters thick. The shallow aquifer is highly mineralized, with total dissolved solids between 1 and 5 grams per liter. It cannot be used as drinking water, and in some places it's even too saline for irrigation use. The shallow aquifer has good recharge of about 20% of precipitation and irrigation water applied, which the deep aquifer does not have. The deep aquifer has no local recharge. A sustainable use of the deep aquifer means zero pumping. Therefore, the deep aquifer water supplied to households and industries has in the last years been substituted, at least partially, by water imported through the South-North Water Transfer Scheme from the Yangtze River Basin, and more is to come. Agriculture still needs this aquifer, which has a very low mineralization. It's very good drinking water quality. But agriculture needs this aquifer in places where the shallow aquifer is too saline and irrigation water has to be diluted with deep groundwater to guarantee yield. For Guangdao, we set up an aquifer management system. It contains 3 modules: a monitoring, a decision support by modeling, and the implementation of measures or policies in the field. The chosen options, after being implemented in the field, we can see their success or failure via the monitoring module in the next year. The cycle is repeated annually. Now, the monitoring module determines groundwater levels, pumping rates, and land use. Groundwater levels are measured by automatic observation wells. Data are transmitted by wireless connection to a central server. The decline of water levels in the shallow aquifer, here shown in gray, has slowed down since 2002. But the decline of deep water piezometric heads has even increased in speed. An item which allows estimates of water use and which is conveniently monitored by satellite remote sensing is land use. Especially winter wheat is easily identified as is the only green thing early in the year. So remote sensing can also be used to check which areas of winter wheat have been fallowed from one year to the next. Now, the third monitored item is pumping from groundwater, and that's difficult. The number of irrigation wells is large. There are about 8,000 wells, and they are mostly primitive wells, as shown here. Monitoring is difficult. So in some regions of China, smart water meters operated with swipe cars have been introduced successfully. So you have a swipe card, you switch on the well, and the data are transmitted by real-time wireless transmission. But in Guangdao, these monitors or these water meters are presently infeasible because of too high cost, and above all, too high cost of maintenance. All wells in North China Plain, no matter how primitive, are powered by electricity. So we decided to use electricity consumption as a proxy for water volume pumped. And with pumping tests, we get the conversion factors. The power supply company installed new smart electricity meters on every single well with remote data transmission once a day. So we know every day the electricity use of a single well. The system is maintained by the utility through its electricity fees. And here are the typical conversion factors. 2.6 cubic meters per kilowatt hour for the shallow aquifer, half or 1.3 cubic meters per kilowatt hour for the deep aquifer, and 11 or 13 cubic meters per kilowatt hour for pumping of surface water from the main canal to the fields. The data go to the modeling module, where water balances are computed and suggestions are made on the 3 measures to contain overpumping. That is fallowing of winter wheat, import of surface water, and water-saving irrigation. Now, a water balance of the county for the time from 2000 to 2014, that means before the project, shows a deficit between recharge and discharge of 22 million cubic meters per year. This deficit is mainly due to pumping from the deep aquifer, which has no recharge. Groundwater use has to be reduced by about 20 to 25% to ensure sustainability. A 2-dimensional groundwater model shows the distribution of groundwater levels. Here you see a depression cone, and it corresponds to a district with a high proportion of greenhouses. These have an even higher specific water use over the year than the combination of winter wheat and summer maize, as they produce throughout the year. The third module is the implementation of policies in the field. They consist mainly of 3 measures: subsidies for fallowing of winter wheat, subsidies for water-saving equipment, and setting of quota for groundwater use, and then water fees will be collected in the case that quota are overstepped. The subsidy for not growing winter wheat is $1,120 per hectare. It is the most successful measure so far, as farmers earn very little from wheat growing. Subsidized water saving is less successful, as farmers already make great efforts to save water. It may become more important when small farms are combined to bigger farms. This is an ongoing process, as the usual family farm with less than 1 hectare does not secure a reasonable income. Young people leave the countryside to make a better living in the cities. Center pivots, as shown here in the picture, are not suited for the smallholder farms. The envisaged quota scheme is 3-tiered. It allows free water use up to the sustainable level, then a water fee of 0.1 Chinese yuan per cubic meter, and finally this fee is doubled for the excessive pumping defined by the 3rd tier. Only greenhouses will fall into this last category. Mind that the water fee is added on top of the electricity fee, which is also about 0.1 Chinese yuan per cubic meter for pumping from the shallow aquifer. I come to my conclusions. Between 2014 and 2019, the water gap has been reduced from the 22 million cubic meters per year to about 1/2. Most effective overpumping control measures are the subsidized fallowing of winter wheat and the import of surface water from the Yellow River. Electricity to pumping volume conversion has shown to be an effective and feasible method for metering of many small irrigation wells in the North China Plain. The water fees for overstepping quota have been calculated, but they are not yet implemented due to the resistance of farmers. They are also too small, really, to have an effect. Water saving potential is low. As farmers already save water by practicing deficit irrigation, it will increase as small family farms are merged to large farms which can practice precision agriculture. The final solution is a combination of fallowing and surface water import. Fallowing is limited by the National Grain Policy grain security. Surface water imports are used very inefficiently today, and their improvement is key to the solution. Now here you see shallow aquifer, we are almost in equilibrium. The task for the future is to also get the deep aquifer into equilibrium. With this, I would like to acknowledge the support to the Swiss Agency for Development and Cooperation, the Chinese Ministry of Water Resources, and the China Geological Survey in this project. I also thank all my colleagues, and I thank you, the audience, for your patience. Thank you very much.
Hello, I am Rien van Genuchten. I will be giving a little talk on some of the issues of water resources and arid environments as part of the international conference. I very much appreciate having been invited to participate. I am been working for many years in California, especially on numerical modeling of subsurface water flow and contaminant transport processes. So I would like to give a little bit of an overview of some of the tools that we developed for this purpose. Right now, I'm partly in Brazil and also have some connection still with my home country here in the Netherlands. I want to first start with what I would call an abstract of my talk, which is a plot that was published in a book by Mary Beth Kirkham about the world population. You can see here that the number of people on this planet were about between about 1/2 billion. But then in the 17th, especially 18th, 19th century, it started going up. This is probably correlated, although I don't want to say that too loudly, with the challenges we have in managing this planet. But we can also, instead of billions of people, we can here then also plot on this scale the challenges we have in terms of managing agricultural, arid environments, freshwater issues, think about pollution and so on. At the same time, we are understanding so much better what's going on. So on this curve also, we could here plot our insight into the challenges we are facing. Think about the science, the awareness, global collaboration, and so on. So this will be an issue whether or not we stay ahead of the challenges that we're facing. I mentioned that I worked for many years at it's what's actually called the US Salinity Laboratory, and our focus was really on agricultural challenges. And then very much connected with that also environmental issues. And so we have been changing the surface of the earth very much. And the focus here would be on the Vado zone. Some people call it also the critical zone, and the more water we include for our groundwater resources. And of course, very important, the vegetation near the surface. And we have been increasing the vegetation or the surface really for in many ways. Deforestation here, you can see agriculture, roads, construction, urbanization. Some other issues here, I'm not going to go through all of them in too much detail. Also, don't necessarily believe all the numbers exactly, but they will give a pretty good idea about the degradation issues of the land surface, salinization, point and non-point source pollution, and so on, urban pollution, of course. But the one thing that I'm very much concerned about is fourth set of issues here, that the the amount of water per capita per year is decreasing quite rapidly. You know, it used to be more than 20,000 cubic meter per year per capita. Now we have barely, or probably not even 5,000. So it's decreasing more and more. And then the per capita arable land for agriculture is been decreasing also very severely from about 0.4 hectare in 1970 to, and they estimate about 0.15 hectares per capita in 2050, which means really that we have to increase the efficiency and productivity of arable land. For me, when we addressed some of these issues, we did a lot of experimentation, but also numerical modeling. And the numerical modeling was based on, and I'm not going to go too much into detail, but there are really three equations that we focused on. One is the Richards equation, actually a pretty famous scientist also at the Salinity Lab where I worked, for water flow in variably saturated porous media, where we have here a number of parameters that reflect how water is being held and the hydraulic conductivity. We also have an equation to address contaminant transport. Of course, there are lots of agricultural chemicals as well as industrial chemicals. Think about nitrogen or pesticides and so on that we try to model using this equation. And then sometimes we also include heat movement. This work over the years has resulted in a number of software packages, the most important one being the HYDRIS models that considers all of these processes at the same time. We also have a Red Sea retention curve, which looks at the description of these nonlinear parameters in the Richards equation, the water retention or PCS curves, and the hydraulic conductivity, which is very much a function of the water content in the unsaturated zone. And then we have a other model that we simplified, where we really look at only advection dispersion, contaminant transport, where we say that the water flow processes are linear, constant flow, and we also look only at water flow. And I'll give you one slide showing a little bit what that STANMOD, so it stands for Studio or Suite of Analytical Models. And the simplest of simple equation that we have is the advection dispersion equation. And we did some experiments here, and then we tried to fit the parameters in this equation, R being the retardation factor that reflects the absorption. In this case, it would be tritiated water, basically like water movement, and hexaphilic chromium. And there would be still a little bit of a retardation of the chromium. This worked well for homogeneous, very homogeneous soil systems, but in many cases we had trouble. So we could not fit necessarily the data with that particular simplified equilibrium model. And this very often occurred when we had a what we call a dual porosity medium, where we have large pores, small pores. In this case, we would have dead root channels or gopher holes, wormholes. But think also about aggregated soils, think about fractured rock and so on, where we would not get these nice sigmoidal breakthrough curves. And then we changed the equation, the governing equations, to get something that would give a better fit. Of course, these models, analytical models, were modified later, 2D, 3D, we included degradation, zero order production, but as long as they were analytical models. More general though, the focus was on our HYDRIS codes that we developed, really worked with these now about, what, 30, 40 years. This gives an overview of the various processes. Again, the Richards equation for transient flow in variably saturated media. Root water uptake, critical in agriculture, but also many environmental applications. Think about global climate, think about evapotranspiration and so on, where we included various processes, including compensated uptake, passive and active solute uptake that would be very important for phyto extraction or phytoremediation problems. And then contaminant transport. You know, many of the processes that we have with agricultural chemicals, and I hate to say, but agriculture has always been the biggest polluter of all, you know. But we try to really understand and minimize the effects of various processes. And so you can see here some of the things that we included in the HYDRIS codes, including virus bacteria transport, colloid and colloid facilitated transport. We coupled the HYDRIS models with the freq-C, so we get a lot of capability in addressing multi-component transport models. Then a few other things. We included, for example, some databases that made it much easier for people to look at real-time problems, some guidance about the PCS or the hydraulic properties here. It's called Peter transfer functions, also for water uptake. and then everything was placed in a interactive graphic-based interface environment, the GUIs. I want to show you one or two different applications. One where we looked at the problems of fresh water. Of course, that goes back to the earlier slide. The challenges are enormous. You can see here two slides, one from some devastated agriculture area in West Africa, another an abandoned irrigated field in Mexico. But these are really symptomatic of many other cases. We even have in Brazil quite a few of these in the northeast of these abandoned irrigated fields. India, Middle East, North Africa. Not only freshwater issues, but also the contaminants. And one of them where we worked and really focused on a lot was salinity. In two cases here, this is a heavily salinized field in Colorado, mostly because of upward capillary flow from the groundwater table from layers that were in a natural way very, very saline. So the water evaporates, the salt stays behind. This is very common in many irrigated areas, in this case with furrow irrigation. So this is in the Central Valley of California. It's at somewhere between Los Angeles and Sacramento, San Francisco, and a little bit higher. But that was there causing a lot of salinity problems you can see here because of a inadequate disposal of drainage water. And so this leads then to the question whether these traditional irrigation methods, especially furrow irrigation, but also sprinkler irrigation, it's a little bit more efficient than furrow irrigation, but not necessarily the perfect way either. But you can see here in the furrow, the water, when you have aggregated soils or soils, when it is saturated, you can have a lot of drainage. You have a lot of interaction with the atmosphere. And so the efficiency of using this water is not the greatest. And so then the question arises whether or not the surface irrigation methods are sustainable. And at that time, we focused very much on alternative approaches, and one especially would be the subsurface drip irrigation. And it was very much popular to look at this in the Central Valley of California, rather than using surface irrigation. And so we have some experimentation, and then you can see here a simulation with the hydroscopes from the drip line in this particular location. We are very much concerned about the shape of the moisture front around the drip line. So if you have a coarse soil, much of the water would go down. It would not necessarily be, let me look at the next slide here, it would not be necessarily a very cylindrical distribution. And here you can see here the numerical and the measured data are very close. For clay soils or fine textured soils, you would get a relatively cylindrical distribution. For sandy soils, coarse textured soils, it would going down much more. Another side to this is not just how to irrigate, but also when to irrigate. And this is actually, I thought it would be nice to also done with the hydroscopes, but where people would irrigate depending upon the stress of water in the root zone. And this is an experiment that was done, as well as simulations by Sharon Simonek and Lazarovich a couple of years ago, where you would place the tensiometer in the root zone, and then you would start irrigating when the tensiometer would indicate a certain stress, in this case about minus 40 centimeters. And then you would irrigate until the tensiometer gives you a value much closer to saturation, and then stop. This is without vegetation, and here with vegetation, if I did this right. You can see here that it is basically automated. And so we have an issue of not just how to irrigate, but when and how much to irrigate. Another one, and I kind of like this particular slide. We worked with Altaf Sial, a friend, colleague from Pakistan, where you can see here they use these pitchers for irrigation. Actually, these pitchers are also sometimes used for cooling their homes. And then the issue was what would be the distribution of water when this was used for irrigation. So the advantage of this is, of course, very, very efficient. You put water in the pitcher, it would slowly move out through the walls. And if you have a good baker, you can pretty much bake the pitchers with a certain permeability of the walls. And of course, this is not larger scale mechanized agriculture, but it's still very useful for legumes and other things. It has been used a lot in North Africa in the beginning, Iran and other places. And one of the issues I thought was quite interesting was if you use small pitchers or the large pitchers, if you would get different distributions. And it was not really the case, as we could show with our numerical simulations. These are issues about freshwater use. I want to show another example, completely different, but basically still with the same idea of looking at water flow and contaminant transport, in this case related to mining and milling operations. Of course, there's a lot of pollution going on also by the mining milling industry. Here are some examples: a copper gold mine, I think it's in Papua New Guinea. In Brazil, we have lots of issues with what we call norms. These are natural occurring radioactive materials. So when people are mining certain chemicals, the natural, the rocks occur some natural radioactive materials, especially uranium. And so there's a concern about whether or not these concentrations are too high. Then also here, a nuclear waste site is also in Brazil that is causing lots of problems. And then a few other data here about these problems also in the US. Yeah. I want to show you one example of this that we addressed with the hydroscopes. This is actually a mining milling complex in Brazil. I'm going to call it the metal and not specify what exactly was being mined to give a little bit confidential information, not to make it too public. But it shows here a complex where the rock was being crushed in this leaching area, and then it was leached with sulfate, sulfuric acid, and then it would end up in the holding ponds, after which they would be processed by the complex itself for whatever the metal were to be. Actually, what they found is one of these holding ponds, the water level, or liquid level, I should say, started decreasing. Very nasty material again, a pH of about 1.5, very high concentrations of the metal. And at first they thought that it was a problem of evapotranspiration or evaporation from the surface, but then they discovered that the geomembrane at the bottom started leaking. And so they had a lot of observation on other wells where they looked at the contaminant plume. The surface plot here, and you can see that actually, when you go back, the line of transport was roughly in this way here, with the origin. And you can see that it was moving here from east to west. And what we did was actually a cross-section. We try to simulate that with a cross-section, both the sulfate as well as the metal itself. You can see here this holding pond where the geomembrane was punctured. We had some clay here. Then we had natural soils, subsurface soil here, a more or less granular aquifer and a fissured aquifer. Think about a slightly fractured rock material. So we tried to simulate that. Here's the sulfate plume that was simulated over a period of 5 years. Here's the observation well that was critical for the metals, not necessarily for the sulfate plume. Actually, when the leak was detected, the sulfate already completely traversed that line between the source and the observation well. But you can see here it goes down, and then it picks up by the groundwater and then moves away from the site. So a little bit stays in the capillary fringe region here in the subsurface. These are some simulations of the metal plume. You can see also it goes down, but the time frame is much, much larger. Stuff moves very, very slow, and then eventually to the right. One of the things, I'll show you in a minute the comparison with some data, but one of the things that we noticed when we did the simulation is that below in the unsaturated zone part, below the holding pond, a lot of material remained, and it would be leaking very slowly into the saturated zone. And this actually was something that could have been used to advantage instead of just repairing the geomembrane and then keep on going. They could have digged this up here and then really minimized future pollution of the subsurface. We call it the shadow of the waste site. Yeah. And these were some comparisons of the simulations with 3 observation nodes very close to the monitoring well. And then here, these are some data that we needed to use to get a dual porosity non-equilibrium type formulation. Not that we would believe necessarily all the simulations, but it gives a little bit of a view of what would happen with the metal in the future. Many other applications, I'm coming very close to the end, that we applied the hydroscopes to it. Here are some applications, but there are really hundreds, if not thousands, of papers now already published about this, from typical agricultural surface drip, sprinkler irrigation, food water uptake again, pesticides, non-point source pollution, reactive waste, landfills. We worked a lot with landfill covers, how to make the system most efficient, highway design, flow around buried objects, and so on, and virus, bacteria transport. I encourage you to have a look at this particular website. There are many, many examples and papers that have been using these hydroscopes, including actually very specific pre-programmed examples. So there's a link here that you can look at if needed. As a summary, environmental problems, we're facing this and we have to address that. And at the same time, we have enormous progress. When we look at irrigation, it started really about 3,000–4,000 years ago, whoever you believe, but you look at the partial differential equations that we developed to describe these things numerically, it's less than 100 years. The Richards equation was done in, 1931. The amount of publications that are being published now, it's enormous. We are aware here, actually, this last one, we are aware of the problems. There's global collaboration, presumably. We have new methods. Vertical farming is becoming quite popular, green roofs. And then all things are site-specific. This is what I want to stress that we are now aware of. When, for example, we look at drip irrigation, it minimizes the amount of water that will be used for crop production, but sometimes you have to be a little bit more flexible about it, because sometimes when you have the drainage, farmers down gradient may need to use also water. So it depends everything what the specific conditions are. Then a couple of other things. Well, this here is reflected by that earlier, remember, graph I showed that everything is increasing. So the problems are increasing, our insight is increasing, and you can see the problems and our solutions. And it really, makes me a little nervous. Are we staying ahead of the problems or not? State of the art, state of the practice. There's a lot of difference still there, not just in terms of topics that or techniques that are being used, but also between disciplines and geographically, and then the future. And then going back to this, it makes me nervous. Everything is accelerating. What's happening 100 years from now? Are we concerned not just about children, but our grandchildren? That's kind of what I wanted to say. Again, thanks the conference organizers for having me participate in this. Very interesting. I think the topics are very urgent. And I would like to leave it by this. So thanks again. And I want to thank also all the collaborators that worked with me over the years in especially the modeling part, but also the applications to various problems. Thanks.
Yeah, good morning. I'm making this presentation. I'm focusing this presentation on some laboratory experimental methods we can use to address some emerging problems in hydrology, water, and the environment. So I had to try to categorize the type of problems the hydrologists and water engineers are involved under these 6 categories. Starting with potable water, the potable water is the sustainability of good quality water is one of the problems, one of the big challenges. And the second one is the global warming, and the global warming has a lot of hydrology and water implications. And the third one is the health, which is related to poor water and the climate issues. And the fourth one is the food security and the water energy nexus. Natural disasters such as floods, droughts, and tsunamis, and potable water and again I mentioned potable water. So all these problems has a dimensions of water. So I want to make a few observations to sort of orient ourselves into this talk. So the numerical models can be used to address some of these problems. So the question still remains how good these models are, these models ability to capture these processes when the processes become very complex. So then how do we validate these models is another question asked. And then what are the characteristics and information which goes into these models? And finally, the issue of scales. When we develop models, we develop parameters at a smaller measurement scale, so observation scales, and try to apply these into larger scale. This is a classical what I call upscaling problems. So the primary thesis of this my presentation is how carefully designed and theory-driven experiments at various test scales can play a central role in providing answers to critical scientific questions, and how they will help to fill knowledge gaps to address emerging problems in hydrology and water. So I want to emphasize the fact that when you do experiments has to be theory-driven. So what this means is that the experiment, before you design the experiment, you need to design the experiment based on a good understanding of the theory. Otherwise, this will be very challenging to interpret the results and make any sense out of the data. So there are many challenging problems in hydrology and water involving interfaces. I'm taking some examples. So first one is the water-air interface, which is we quite familiar with, which is the water table. And the second one I'm showing here, the saturated and the unsaturated zone first interface. Second one is a saturated unsaturated water interface, which is the water table. And the third one, the river aquifer interface, which is when you're modeling rivers and aquifer like conjunctive use, surface subsurface management, this interface become important. And the fourth one is the water, water, and in this case, non-aqueous phase liquid interface. So this has to do with trapping of chemicals and like supercritical CO2 in subsurface carbon sequestration. And then the next one is land-ocean interface, and then land-atmospheric interface, and snow and atmosphere interface. So these are all happening at interfaces. So I'm going to, in my talk today, I'm going to focus on two of these interfaces, the water supercritical CO2 interface and land-atmospheric interface. So to introduce the methods I have been using, I'll use this figure to explain. On the left-hand side, you have the pore scale. So all the fundamental processes we like to understand happen at the pore scale. And always to remember that the pore scale is three-dimensional. And then the field is also three-dimensional. And then the whole idea is to understand how do we use this understanding of what's happening at a smaller scale and to apply to 3D field scale using models. So as you see that the problems get complex as you go from the pore scale to the field phase. So in this particular figure, I'm showing two zones. The light blue zone is the atmosphere, because one of the problems I'm going to be looking at involves the atmosphere as one of the domains. And the second problem is the porous medium. So that is below this line. So if you look at the porous medium, the complexity of the problems in the porous medium come from the dimensionality, because most of the time we do experiments. So we do experiments moving from this scale to this scale. We do experiments in using 2D models, 3D models, 1D columns. Similarly, we do 1D models, 2D models, and 3D models. So that the dimensionality becomes very important, that because when you characterize the system using 1D experiment, how do I use that information in the 3D field? And second one is the heterogeneity. So subsurface is naturally heterogeneous. And then when you try to model this in the field system, we have to use heterogeneity. And in the atmospheric system, the atmosphere is always three-dimensional also, but atmosphere is material-wise very homogeneous, but it becomes heterogeneous because of the vapor and thermal processing. So what I'm going to talk about today is a scale called intermediate scale. This is the scale I believe we can do, actually we have shown do interesting experiments to address the problems of the 3D field, as well as how to move from this scale to this scale. So the intermediate scale is a scale intermediary between the column and the field scales. And we normally define the scale to be 1 to 10 meters. So this is a scale where the field scale processes can be mimicked under controlled conditions. So this is some of the test facilities we have been using in our research. These are three-dimensional and two-dimensional tanks, and then we have various control systems. There are a lot of sensors, and we can control the boundary conditions, initial conditions, etc. So there are 3 points I want to make in this particular slide. So when you develop models, these models are some sort of partial differential equation where the initial conditions and boundary conditions have been known. So in the field, it's very difficult to control an initial condition, boundary conditions, especially if you are trying to develop databases to validate theories and models. We need to have a really good understanding, good quantification of the initial and boundary condition. And the second issue is the characterization. So when you go to the field, especially in the subsurface, it is very difficult to characterize these systems. Whatever information you obtain to design heterogeneity come from cores or wells, and these are always going to be spaced apart. If you're looking at very large systems, you won't have all the data. So the third one is the third point I want to make is that it's very difficult to get precise data in the field to get a fundamental understanding of these problems. So I'm going to take two timely problems related to global warming and food-water nexus to demonstrate how this type of test can be used to address challenges and capitalize on some opportunities. The first example I'm going to take is on carbon sequestration. The carbon sequestration is to mitigate greenhouse gas loading into the atmosphere. And the second one is the opportunities. So I'm going to look at the problem of energy and mass thrust on the atmospheric interface as applied to climate change. So this particular figure you see on the left-hand side come from the IPCC 2005 report, where they identify the different mechanisms of trapping. So the idea here is that you take CO2 and then you inject into deep saline formations with the expectation that this is going to stay there for thousands of years, and that way you take the gas which is normally going to the atmosphere into the subsurface. So you can see the injection period can be about 20 to 40 years, and the post-injection periods may be hundreds of years. And then we are looking at this system to stay 1,000 years. So you can say 4 types of trapping mechanism: the structural trapping, and the residual trapping, and the solubility trapping, and mineral trapping. So actually I'm going to focus more on the structural trapping today, so just to demonstrate how the experiments can be used to address some of these problems. So this particular figure you see down here is actually from the world's first commercial site on carbon storage. And so this one, actually they had taken pictures of this the evolution of this trapping process. And the idea here is that if you have a very fine formation and a coarser formation, and there's a transition of the interface texture, then due to capillary barrier effects, this fluid going to get trapped. So this is basically what's happening in this system. So the objective of this particular example I'm going to take is to say how we can use this entrapment mechanism or the heterogeneity to our advantage to increase trapping. So in the case of carbon sequestration, the heterogeneity can be used to advantage, but in the case of non-aqueous phase liquids like groundwater contamination due to petroleum-based solvents, that problem we like to take the contaminant out as much as possible, because it's going to stay and become long-term source of contamination. So this particular experiment I'm going to describe here is conducted in an 8-foot long and 4 feet high tank. It's a 2-dimensional tank where we pack the tank with a completely homogeneous, because I'm trying to make the argument that with the heterogeneity I can enhance entrapment. So in this particular case, one of the challenges in this problem is that when carbon CO2 is injected into the subsurface, it is behaving like under the subsurface high pressure condition is going to stay like a fluid. But when you try to do this experiment in the ambient condition in the lab, it is going to be a gas. So some of the literature people who have done this type of work, they do these control experiments in the laboratory and ambient laboratory condition by using very high artificial pressures to keep the fluid as a liquid. So what we have done here is actually we have selected some what are called surrogate fluids. So these fluids, we can select these fluid combinations in a way that we can use the viscosity ratio and other dimensionless groups, so that this fluid combination under ambient laboratory conditions behave like what you expect in the field. So we have actually demonstrated this using models where we simulated the real supercritical CO2, and then we simulate our analog fluids, and we will get the same results. So in this particular experiment, what we did was we filled the tank with a homogeneous soil, and this is a cap rock, and we injected this analog fluid at the bottom, and then there's another second fluid which is acting like the brine, and then when we inject it, and because supercritical CO2 is a lighter fluid, it actually migrates upwards by buoyancy, and they started moving horizontally this way. And then now the second figure is where we pack the same tank with a spatial correlated random field. We took 5 soils of different hydraulic orders of magnitude different hydraulic conductivity and use some geostatical parameters and create this random field. And we took the same amount of fluid here and we injected it. You can see just visually looking at this figure, you can see that in this case, the homogeneous case, the fluid just escapes and then got out of here. And in the previous case, in this case, it got trapped in these pools with high saturated pools. So in our laboratory, we have actually a way of measuring these things, quantify these things using what we call using an X-ray attenuation system. We shoot X-rays to the tank, and then we can actually get these nice saturation profiles. As you see from the color from this homogeneous tank, most of the fluid actually really escaped here. So you can look at this situation as some sort of fracture in the cap rock with this escape. Now you can see here, this is stably entrapped and this didn't move. This is the same volume got trapped in this case, and you can see very high saturations at these locations. Okay, now to interpret these results, what we did was in this particular graph, I took the tank vertically so I can define the length along the tank from the source, from the point of injection along the tank this way. And then I took the center of mass of this plume. So the center of mass will tell you how fast the total mass of the system moves. So I'm plotting the center of mass, location of the center of mass on this axis, and then on this axis I'm looking at the time. As you see, when you start, the injection started here, center of mass was here. As time goes, center start moving up, moving down, and as you see this way, the saturation, the center of mass goes down because it's it's smaller and smaller and smaller. I'm saying larger and larger and larger because actually this is a negative number. And as you go down here, then at least about 1500 hours, in 1500 hours, it's completely stopped. So this is completely immobilized after 15 hours. So actually we ran this experiment. This experiment stayed about 3 years after this experiment was done, and still we saw that nothing had mobilized. So this is a good thing. So we were able to actually show that the entrapment can be enhanced by using heterogeneity. So actually we have done other work trying to develop injection schemes to using the same ideas to see what is the way, how do we inject things so that we can capitalize on this heterogeneity. So I'm going to go to the second example, which is to do with the mass and the energy transfer for the land-atmosphere interface. There are a number of problems which involve this interface, but I'm going to focus on this one problem, which has to do with the climate change. So this is actually so this problem has to do with land atmosphere, plant atmosphere continuum, food security. If you look at this map, I'll get back in a minute, but you can see that one of the drivers for this studying this problem is that the global population is going to increase, and then due to climate change, some of these areas in the world are going to have very high water scarcity, and then you can see that food production need to increase by 60% to meet this population needs, global needs, and then by 2030, these 2/3 of the global population will also be suffer from effects of increased water stress. So you can look at this map, you can immediately see some of the high water stress areas are also the areas where they are going to have very high needs of food. The food security is associated with part of Africa and parts here. So also there's another interesting observation is that the family farms produce 80% of the world food. So if you can find a way of making water efficient in these small farms, then actually this can have a fairly large impact. So for this, we actually, to develop this idea, so we actually published a paper on this National Academy paper where we talk in more details, and if you're interested, you can read this paper. But the idea is here, that if you go to Arid zone, and some of these pictures are taken at different parts of the world, you can see the plants seem to be randomly distributed. But if you look at the distances, their average distances have some correlation to the climate and available water resources. So what we thought was that what is the reason for these plants to grow in this spacing? So this is an experiment we could do in the laboratory to do this experiment in the laboratory, I will talk about in detail. So when two plants grow, we need to understand the plant-plant interaction, the theory behind this. So there are three types of interaction which are listed here. And then these interactions, when the plants grow, the interaction occurs above the ground and below the ground in the intercanopy region and the root zone. So this interaction can be positive or negative. Positive interaction is called facilitation. In this case, what it says is that it's beneficial. So these positives are beneficial and improve the performance of one plant from the other one, and negative, the two plants are competing. So this is observed in the plant communities. So to study this problem using the experiments, so we developed this very unique experimental facility at Colorado School of Mines, where basically you have this 8-meter long soil tank, which is the intermediate scale size I talked about earlier, and then this circulation wind tunnel, where we control the boundary conditions, atmospheric conditions, we can control the wind velocity, we can control the temperature, and we can control the relative humidity. And we can measure very accurate data on the subsurface as well as the atmospheric system. So we ran these experiments in this system. So to do that, because it's very difficult to study model plants, hydrodynamics around plants, what we did was we wrote a paper on this to see whether we could use an analog of a plant. Again, this is a challenge in some of this experiment. So what we did was we took a limestone block and we took a plant and we ran the same experiment, these two blocks, and we basically showed that the limestone block can simulate the evapotranspiration process fairly reasonably well. So the idea here is when the plant takes the water, it transfer to the leaves, and here the limestone block by capillarity take the water out and takes out. So what we did was we ran 3 experiments in this particular case. In the first experiment, we actually spaced this plant, the two blocks, 50 centimeters apart, second one 45 centimeters apart, third one 105 centimeters apart. So we can make a lot of measurements in the atmospheric systems, relative permeability, temperature, wind velocity, Y and Z component, the wind velocity, and the underground we can measure again temperature and soil moisture. In this particular graphs, I'm showing the relative humidity above. This one is in the atmospheric boundary layer, and this is below the soil. And you can see that immediately when these plants are very close to each other, you can watch the 25% relative humidity curve in these 3 graphs. You see they are quite different depending on the spacing. And similarly, you can see the soil moisture distribution become different depending on the spacing. And then the important thing to notice here is that both when these plants are close to each other, they have these influence zones of the plant which intercept with each other, and in the case of subsurface, the influence zones also intercept. So there are some implications of this. The idea here is that what is this out of these 3 cases which produce the most efficient use of resources by these 2 mechanisms of facilitation and competition. So to do that, actually we took this data and plotted this graph, where on this axis you have the soil moisture, on this side the time, and on this is again, in this case, what you see here is this is the shortest spacing, the 15 centimeter, this is the intermediate, this is the largest spacing. You can see immediately that when you look at the soil moisture, that the intermediate spacing actually preserves the water the best in this case. So what we did was we plotted the soil water availability for these 3 scenarios as a function of this plant's spacing plant height ratio, where we can classify the atmospheric conditions in these different types of flow situations, skimming flow, interfering flow, and isolated roughnesses. And we found that the facilitated dominated this zone gives the highest spacing. Okay, so this is basically some general conclusion. The experiments and the intermediate scales are challenging, but provide many opportunities to address globally important problems, and driven by good theoretical foundation, innovation, and patience, and utilize new instrumentation and sensitive technologies to allow us to do very exciting experiments. And finally, I want to make the point that some of these complex problems cannot be solved just by doing modeling. It's an iterative process where you do modeling, go to the field, go to the lab, and you can learn from each of these things, and you keep iterating until you solve the problem. So finally, I try to thank my students and collaborators and the funding agencies. And finally, I like to make this opportunity to express my gratitude to PSI-PW for recognizing the Water Scientists and Engineers Board and the board global impacts makes. Personally, I have benefited. This is one of the talks I'm giving after I got the Groundwater Awards 4 years ago. Actually, I was able to use this funding to do very interesting projects, which includes helping students from developing countries to go to universities, and I'm doing some work in South America looking at some water issues. So this is really a good opportunity I got because funding, and I really thank for the foundation for providing this type of support. Thank you.
يرفع رئيس الهيئة الإشرافية العليا للمؤتمر المشرف على معهد الأمير سلطان لأبحاث البيئة والمياه والصحراء وأمين عام جائزة الأمير سلطان بن عبد العزيز العالمية للمياه الدكتور عبد الملك بن عبد الرحمن آل الشيخ وجميع الجهات المنظمة للمؤتمر والمشاركين فيه جزيل الشكر والعرفان والتقدير إلى مقام خادم الحرمين الشريفين الملك سلمان بن عبد العزيز يحفظه الله على رعايته الكريمة للمؤتمر وعلى دعمه أيده الله وسمو ولي عهده الأمين صاحب السمو الملكي الأمير محمد بن سلمان بن عبد العزيز يحفظه الله لكل ما من شأنه رفعة هذا الوطن وتقدمه وتطويره في كافة المجالات وبما يحقق أهداف رؤية المملكة 2030. يوجه رئيس اللجنة الإشرافية العليا للمؤتمر وجميع المشاركين فيه جزيل الشكر والتقدير إلى معالي وزير البيئة والمياه والزراعة المهندس عبد الرحمن بن عبد المحسن الفضلي لحضوره حفل افتتاح المؤتمر نيابة عن خادم الحرمين الشريفين الملك سلمان بن عبد العزيز يحفظه الله. كما يوجه رئيس اللجنة الإشرافية العليا للمؤتمر وجميع المشاركين فيه جزيل الشكر والتقدير إلى معالي رئيس جامعة الملك سعود الأستاذ الدكتور بدران بن عبد الرحمن العمر على دعمه لكافة الأنشطة التي ساهمت بعد توفيق الله في نجاح المؤتمر وتميزه على الرغم من الوضع الحرج الذي تفرضه ظروف الجائحة الوبائية والاضطرار إلى استخدام وسيلة التواصل المرئي عن بعد بدلا من الأسلوب التقليدي المتبع في الدورات 8 السابقة. كما يوجه رئيس اللجنة الإشرافية العليا للمؤتمر الشكر الجزيل لضيوف الشرف وجميع الشخصيات رفيعة المستوى والعلماء المبدعين الذين ساهموا بتقديم موضوعات ومحاضرات علمية متميزة بل أثرت المؤتمر وساهمت بشكل كبير في نجاحه وشكل هذا التجمع للنخب المتميزة ظاهرة استثنائية فريدة من نوعها. ويوجه رئيس اللجنة الإشرافية العليا للمؤتمر وجميع المشاركين فيه جزيل الشكر والتقدير إلى الجهات التي دعمت المؤتمر ومنها جامعة الملك سعود وجائزة الأمير سلطان بن عبد العزيز العالمية للمياه من خلال مؤسسة سلطان بن عبد العزيز آل سعود الخيرية وشركة أراسكو الشريك الاستراتيجي وأمانة المنطقة الشرقية الراعي الذهبي. كما يوجه رئيس اللجنة الإشرافية العليا للمؤتمر وجميع المشاركين فيه جزيل الشكر والتقدير إلى جميع لجان المؤتمر ومنسوبي معهد الأمير سلطان لأبحاث البيئة والمياه والصحراء ومنسوبي الأمانة العامة لجائزة الأمير سلطان بن عبد العزيز العالمية للمياه ومدير ومنسوبي إدارة العلاقات العامة والإعلام في الجامعة ومدير وخبراء مركز التعاملات الإلكترونية في الجامعة ومؤسسة الفريق المنظم للخدمات التجارية إيفنت تروب التي نفذت المؤتمر والمعرض الافتراضي بالاعتماد على منصة في فيرز وجميع من ساهم في الإعداد للمؤتمر على كافة الجهود الكبيرة والمميزة التي بذلوها وساهمت في نجاحه. وقد جرت العادة أن تتضمن الجلسة الختامية التوصيات التي تعدها اللجنة العلمية للمؤتمر بناء على ما يصلها من المتحدثين في الجلسات العلمية، إلا أن ظروف انعقاد المؤتمر بالأسلوب الافتراضي أدت إلى صعوبة تجهيز هذه التوصيات في الوقت المناسب. لذلك نتوجه إلى جميع المتحدثين والعلماء والمشاركين في المؤتمر برجاء تزويدنا خلال أسبوع بتوصيتين أو أكثر تنبثق من الكلمات التي ألقوها في المحاضرات التي قدموها في هذا المؤتمر عبر البريد الإلكتروني للمعهد psiewdr@ksu.edu.sa. وفي الختام وبسبب نفس الظروف التي أشرنا إليها فإننا لم نتمكن من استقبال الأسئلة من الحضور والإجابة عليها من العلماء المحاضرين. لذلك نأمل ممن يرغب من الحضور الكرام توجيه الأسئلة أن يرسل خلال أسبوع عبر البريد الإلكتروني للمعهد psiewdr@ksu.edu.sa صيغة السؤال بوضوح مع ذكر اسم المرسل وبريده الإلكتروني واسم المحاضر الذي يرغب توجيه السؤال إليه. وسنعمل على توجيه هذه الأسئلة إلى المحاضرين الكرام ونأمل منهم الإجابة عليها خلال أسبوع لنتمكن من نشر الأسئلة والإجابات في موقع المؤتمر www.psiwrae.org لتعم الفائدة منها. نستودعكم الله ونأمل أن تتعافى الأرض وجميع سكانها من هذا الوباء ومن كل داء وبلاء، والسلام عليكم ورحمة الله وبركاته.